So all of us right now are staying at home, or rather we're forced to be staying at home. And it's a rather interesting situation that we're in right now. A recent initiative I've heard, uh, several academic institutions, universities, you can say, in light of this whole thing going on, uh, they've actually, pretty cool thing they did, they actually made their books, their university textbooks, those kinds of things, they made it all publicly free. I don't know which specific ones did that, but I know Cambridge made its whole library free, and you can all access and download it for a limited time until the quarantine situation ends. And I think it's a pretty cool initiative to try and get people to study more instead of just doing nothing at home and being bored and stuff. But yeah, I mean, if you want those books, you can probably just search online. I'm sure someone has made news about it, wrote an article or a blog, compiled a list of universities that have been doing the same thing that Cambridge did, and you can get those books for free. Or, of course, you can use LibGen. That also works out because all the books there are also on LibGen anyway. But yeah, I mean, they're more easily accessible now. Well, well, in a situation like this where you're bored and I'm bored and both of us are bored, why not let me teach you something and maybe you can in turn hopefully learn something. I'm going to be talking about math, some pretty interesting thing. What I'm drawing right now is the Harmonic series, which is just a continual series of fraction with the bottom part. I forgot which one's the bottom part, the numerator or the denominator. Forgot which is which, so I'm gonna just call it the bottom part, where the bottom part is continually decreasing all the way until infinity. And surprisingly, blah blah blah, this thing actually goes over to infinity, although it's decreasing. But if you add all of them up, it's gonna go to infinity. Lesser known, however, is the alternating harmonic series, which is essentially the same thing, but with the positive signs here alternating between negative and positive. Now, something cool about this series is, unlike the regular harmonic series, which goes on to infinity as you keep going, this thing actually this thing actually converges to a limit, which I will later show and prove is ln 2. So yeah, it's pretty cool and interesting how when you turn the even when you set the even terms as negative, just like this change here made it go from infinity to ln 2. It's just cool, interesting, and just random. And hopefully in the next few minutes or hours, I don't know, depends on how well I explain things, we're gonna learn why the alternating harmonic series converges to ln 2. And I'm going to show that to you with two different methods. The first method is actually a quite difficult one, but it is rather interesting because it explores different areas of math, like Like when you compare it to the second method is, I don't know how to describe it, like really shallow in terms of exploration, while the first method is goes down much deeper in trying to search for the answer. So we're going to start with the first method and we're going to show how we can do the exact same thing in an easier way. Right off the bat, we just wanna understand why the alternating harmonic series is convergent, because we just okay, first things first, we just wanna prove that the alternating harmonic series actually converges to a limit. And there is a test that does exactly just that. And conveniently, it is known as the alternating series test. And it states that if you have a series and it's alternating like this, and then you have a sub p, for example, basically, if the series is decreasing, that means the next term of the series. So we disregard the negative one here. We were only looking at AP. So basically, what we want to check is if this AP, if the next term in the series AP plus 1 will be less than AP. And that would mean that the series is decreasing because every time you go from P to P plus 1, that number will be lesser and will keep going less and less and less and less and less. And this can be easily identified from our series here. We have 1, we have 1/2, we have 1/3, ignoring the negative and the positive, 1/4, 1/5, 1/6, and it's definitely decreasing for all these numbers. Second thing we want to find out is to check if the limit of AP, I'm just going to draw it on top here, if the limit of AP as P goes to infinity is equal to 0. We have to check if AP goes to 0 as P goes to infinity, and the AP, which is this component, is definitely going to 0 as P goes from 1, 2, 3, 4, 5, 6 all the way till infinity. We have 1 over infinity, which we can assume to be 0 because they're just, so close already. We can assume that safely. I also want to explain why the alternating series test works. So if we have an alternating series test where, it's positive, negative, positive, negative, positive, negative, we're going to end up with a partial sum, Sn, going something like this. We have n0, which is no term at all. That's why it's 0. We have n1, which is just the first term, n2, which is the first term plus the second term, n3, which is the first term plus the second term plus the third term, and so on and so forth. The first condition in the alternating series test, which shows that a p plus 1 is less than a p, shows that with each addition, you're just going to make a smaller and smaller and smaller change each time. So the first change will be this here. This here is caused, this is a 1, and this here is caused, and this drop down right here is caused when you add a 1 with a 2. And then the next increase is when you add a 3. So each change you make is going to get smaller and smaller and smaller because each term you add, as we have proven, is just going to lead to smaller and smaller and smaller changes. Therefore, everything on the line here will fit between the boundary of A1 and A2. Nothing will be able to leave this barrier because each change you make is just going to keep getting smaller, and nothing will be bigger than the change you make with A2. Everything following that will be smaller and smaller and smaller. Third thing, wait, no. The second thing that you do with the alternating series test is you check if the limit goes to 0. So like if the limit of AP tends to 0 as it goes to infinity, then as we can see, A2, A3, A4, as we go on to infinity, these changes, these ups and downs, they're all eventually going to become so small, so minuscule, that they're going to become 0 and just end up being a flat line sooner or later. And that's a sign that it converges. So like take an example that the limit goes to 1 instead. So eventually A2, A3, A4, it's all going to drop down as it keeps as the numbers keep getting higher. As we move from left to right, it's going to drop down, but it's going to stop at 1. Even if you zoom ahead towards the right, this value is still going to become 1. And there's no way it's dropping further than that. That's the limit. So as we go to infinity, as these A values drop and drop until it goes to 1, what we'll see is changes that goes up by 1, down by 1, up by 1, down by 1, and that thing is not going to change because even after an infinite iterations, it's still going to go up 1, down 1, up 1, down 1, up 1, down 1. So it's important that it goes to 0 so that it converges into a straight line. There will be no more up and down because those ups and downs will have no value to them because the limit eventually will reach 0. So it's important that it does reach 0 so that there will be no effect. And it's important that it gets lesser and lesser and lesser so that we have this gap here. So we know that it converges somewhere within this gap. And it can't suddenly go higher or lower than that. We know that it's going to be staying stuck here. So since the alternating harmonic series follows that same rule, we can assume that the alternating harmonic series converges. We just don't know what it converges to yet. So right now we're gonna start with the method. And first, I'm just going to write the alternating harmonic series in a different way. We have the sum here, and we're going to denote this with 2n, and we'll see why that's clear in a few moments. So as we said before, the alternating harmonic series consists of positive odd terms and negative even terms. So we can have a summation here that basically goes from we have n here at the top, and we have p equals to, with p equals to 1, and we have 1 over 2p minus 1. So this is the odd terms, and then we subtract it with all the even terms. P equals 1 over 2p all the way up to n. So over here, we can just write this as, well, when p equals to 1, it's 1 over 2 minus 1, that's 1. We have the second term of it, which is 1 over 4 minus 1, which is 1 over 3, and 1 over 5, and so on, n times. And we have the subtraction of all the even terms, minus 1/2, minus 1/4, minus 1/6, n times again. We have this n times again. So in total, we have 2n terms. That's why the sum here is 2n, and why each individual of this can add up to form 2n like that. And this is exactly the same as the alternating harmonic series. We just have to move this over here, move this over here. It's not going to change the value at all. It's all exactly the same. Now, we're just going to remove this part here. And get rid of this. Now what we're hoping to do for this method is we want to rewrite all of this thing here in a way where we can actually come up with an answer. So first we're gonna look at this thing here, which is odd numbers. We want to rewrite it in a different way, and it's possible to do that if we get the sum of all numbers and just simply subtract all the even terms away from it. So if you have 1 plus 2 plus 3 plus 4 plus 5, we have all the sum just regularly lined up like this. If we subtract the even terms away from it, then all we're left with is the odd terms. We can rewrite this in a similar way. We want to get the sum equals to 1 of 2n, because we're taking the entire range of numbers right now of 1 over p. So it doesn't have to be odd, it doesn't have to be even, it's just a regular line of numbers. And we subtract that with all the even numbers, but not all of it, just half of it, because remember we have 1, 2, 3, 4, so we just have to subtract 2 and 4. So this number is half. This has 2 terms, n equals to 2. This has 4 terms, n equals to 4. So we just want to get half of, so the amount of even numbers we need is just half. That's why this is 2n and this is n. I hope that's clear. So this will be even numbers right here. We convert this into this, and we subtract, again just copying this part down here. E equals to 1 and 1 over 2e. And we're going to simplify this further. As you can see, this thing over here and this thing over here, they're exactly the same. We can rewrite it again as minus 2 of the even terms. And 1 over 2, well, this is basically same as saying 1 over 2 times 1 over p. And 1 over 2 over here is a constant, so it can be brought out. And what happens when it gets brought out? The 2 and the divide by 2 will cancel, and it just leaves 1 over p. So let's rewrite this again. And remember that this is all the sum of 2n, or the alternating harmonic series. So it's actually, so we managed to rewrite it in a different way, and the meaning is pretty cool. This is the alternating harmonic series, meaning 1 minus 1/2 plus 1/3, so on, so on. And this is actually equal to the sum of, this is actually equal to the positive sum of the string of numbers, so the signs won't matter. 1 plus 1/2 plus 1/3, so on, so on, so on. Minus by, the same thing. We notice that the 1 over p here and 1 over p here is the same, and it's subtracted by the same thing. But it's only half the length because you only include half the terms. So if this goes on for 100 times until 1 over 100, for example, this will only go for 1 over 50. And you subtract it together, and we get, and in the end, we're going to get 1 over 51 plus 1 over 52 plus 1 over 53, and so on. And that's going to be the same as if you alternate this, and that's going to give the same result as if you're alternating 1 minus 1/2 plus 1/3 up till 100 times. And ideally, we want to use really big numbers up till infinity in order to get the limit of this function and the limit of this function. We have defined this function in a really special way, and it's cool that it works out to be like this. However, we have no way of calculating the exact value. Again, this is just an approximation. Ideally, we want n to be infinity. Ideally, we want the n to be a limit and not just be a number like 50 only. Ideally, we want it to be infinite. Setting n as infinity allows us to get an exact value for the alternating series here. Unfortunately, if we set n as infinity, this thing is just going to keep going on and on for infinity, and we don't know how to calculate that either. So we're going to try do something now. We're going to find a different expression for these summations. And once we can convert these into different forms, then maybe we can write this in a different way too. That will make things easier so that we can get the answer right over here. So to start going on with that, we're going to take a look at the example of a series where the first term is 1, the second term is the integral from 1 to 2 of 1 over x dx. The third term is going to become 1/2, and the fourth term is the integral from 2 to 3 of 1 over x dx. And you might think, oh, it's really weird, and yeah, it is weird, but just focus and concentrate a bit as we deal with this. These values a1, a2, a3, a4, they make up a harmonic series. So 1 minus the integral plus 1/2 minus the integral plus 1/3 minus the integral, and so on. These form an alternating series. And the odd terms right here, a1, a3, a5, and so on, is going to become the harmonic series. They're the exact same terms of the harmonic series, while the even numbers are the integrals. And if we were to write this series 1 minus 1/2, 1 minus the integral from 1 to 2 of 1 over x dx plus 1/2 minus 2 over 3 1 over x dx, so on and so forth, we'll actually know that the series is convergent because of the alternating series test. So firstly, we need to check two things: that the series is decreasing and the limit eventually goes to 0. In this and this will be quite easy to check. We're gonna take a look at a graph right now. This graph will be y equals to 1 over x. As you remember from calculus or whatever, the integral is basically the area of the graph. In this case, from 1 to 2, from 2 to 3, and so on. So we have x is 1, x is 2, x is 3, x is 4. So this area right over here, that's our A2 term. And this area over here, I'm just going to use a different color, and that changes every single color. So I can't do that. Hold on. Oh yeah, I can. Okay. And this color over here, we're just going to say that this is A4, because this is 1 to 2, this is 2 to 3. This is the integral from 1 to 2 and 2 to 3. Now how about the sums? The sums here actually approximate the areas of this graph. For example, we have, just going to use a different color again, A1 is equal to 1, A3 is equal to 1/2. Well, A1 is, well, first let's look at the points here, and here, and here. Y is 1 over x, so this point is 1. Y is 1 over x, so y is 1 over, this is the x-axis, this is the y-axis. Y is 1 over x, so when x is 2, y is 1/2. So this right over here will be 1/2, and over here it's going to be 1/3. Now A1 is an approximation of the area. So we say that A1 is, a rectangle. Wait, no. A1 is a square of height 1, and that checks out from here, and of a length 1, which checks out from here. So this thing here, this green thing here, is A1. Now, A3, on the other hand, is 1/2. So that corresponds to a rectangle with a length, with a height of 1/2, which is over here, and a length of 1, which is the distance between 3 and 2. So we have a box here and a box here. So what do we have? We have A1, which is this big box over here, and that's bigger than A2. A2 is the blue shaded area. So that's smaller than the box of A1. And what do we have after that? We have A3. A3 is this green box over here, is smaller than the blue thing. And then when we go to A4, A4 is going to be even smaller because it's going to be inside the box. So as you can see, these terms A1, A2, A3, A4, they just keep getting smaller and smaller and smaller again. First the box, then the actual shape under the box, a smaller box, the actual shape under the box, a smaller box, the shape under the box, so on, so on, so on, so on, and this graph here keeps decreasing, so the shape of the box and the shape of the curve underneath it also decreases. So it checks out that this function is decreasing. And similarly, it also checks out that the limit to infinity is 0, because when you go so far ahead, this line is going to drop down to some point y equals to 1 over infinity, which is 0, and eventually the area of the box and the area of the line is just going to be so small, it's going to just assume to become 0. And when that happens, the limit becomes 0. So we have achieved the second condition for these series to be convergent. So yeah, we have proven that this thing is convergent. And now let me rewrite everything so it doesn't get messy again. Alright, we know that the series is convergent. We have 1 minus, we'll just write it in a different color just to make things easier. 1 to 2 plus 1/2 minus 2 to 3 1 over x dx. We have this going on and on and on and on again. We can move all the positive terms. Remember, all the positive terms are a part of the harmonic series. So we move all the positive terms together and we move all the negative terms together. So in the end, we can write this as 1 plus 1/2 plus 1/3. All of these is positive and all the integrals are negative. So we can say minus, and this goes on and on and on, and minus by the integral from 1 to 2, 1 over x, minus 1, 2 to 3, 1 over x, so on, and so on, and so forth. So we have from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on until infinity. If you look at the graph, we have the area from 1 to 2, area from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6, from 6 to 7, from 7 to 8, and if you keep going from infinity, that's the same as the integral from 1 to infinity of 1 over x dx. So let's rewrite the orange term over here as integral from 1 to infinity of 1 over x dx. And we can write the sum over here just as a simpler summation thing here. We have these two things subtracted together. This is just a series over here in a condensed form. That's going to equal to a constant because the limit converges to a value. It converges to a value because these two conditions are checked. Remember that. It converges to a constant. And this is a finite constant because converges to a constant. It's a finite constant. So it's a number like 2 or 3 or 4 or 5. We just don't know what it is yet. Later as we move on, we'll find out that the value of this constant doesn't matter because it's just going to cancel itself out later on. And we'll see that happen in the next couple of minutes. But for your entertainment and curiosity, this constant here is known as the Euler-Mascheroni constant, and this value is actually 0.577. Although we have no way of actually calculating and achieving that value and answer right now, it doesn't matter, as I've said before. So we're going to keep moving on. We're just going to assume that it's some constant. And we want to find the value of the summation over here. So we're going to move this integral to the other side. We rewrite everything again. After the integral moves towards the other side, this will be equal to the constant, which we're just going to write as red, minus by the integral from 1 to infinity of 1 over x dx. Let's answer this integral. Okay. What's the integral of 1 over x dx? That's log of x. So that's the same as saying log of infinity minus log of 1. And log of 1 is 0, so it's basically just log of infinity. I'm sorry it's add because it's negative first, and you add it. So it's actually rather interesting because both of these, they will go on to become infinity because this is the harmonic series. It diverges, so it goes to infinity. Then infinity is just going to be infinity too. But interestingly, we see that this infinity is bigger than this infinity because you have to add something towards the right side to make it equal. That means the right side is a bit smaller to begin with, even though both of them reach to very big numbers like infinity. This infinity is still bigger than this infinity. So like this thing over here, it goes up like this. Let's just use it blue color to make the symbol better, to make the symbolism better. The blue thing goes up like this, but the orange one of Lun goes like this. So both of them go up to infinity, blah blah blah. But the orange one going is going at the same direction to infinity, but it's just slower, much slower. And we know that it's lacking behind by 0.577. These two distances, these two speeds are just 0.577 apart from each other. And it's apparent why the summation here is bigger than Lun, because as we've seen from the graph, the boxes here are always going to be bigger than the area underneath the graph. The sum will always be bigger than the integral. Although both of them seem to reach towards a similar value, like they're just going on and on like that. They're both reaching to a similar value. But still, if you look at each thing piece by piece, the log over here, the sum over here is always going to be bigger by this much, by this much, by this much, by this much, always till the end. So blue thing, the sum, always bigger than infinity, even though both of them go to the same direction, that is infinity, and ln infinity is lacking behind by 0.577, which is cool if you think about it, like a race. It's like a race between ln and harmonic. It's like a race between ln and harmonic, and they're chasing each other like this. But then, yeah, ln is lacking behind, unfortunately. So back to the topic at hand. We now have an expression for the sum of 1 over p. We can write this thing over here, in terms of c and ln infinity. And once that happens, we can actually, like do stuff with it. It's cool. We're just gonna remove the bottom part here, get some more space to work with. And firstly, just wanna rewrite this in a way that's better, because we can't directly substitute it at first. We wanna convert the infinity to n's. And we wanna say as n goes to infinity. Oops, forgot to write a 1 here. So yeah, this thing is same as this, agreed. Yeah, no problem at all. So over here, we also ideally want this as n1. We also ideally want this as n approaches to infinity. So both of these hold when n goes to infinity. So this we can substitute it. We just have to say it's c plus ln infinity. Let's use the appropriate colors as well. C plus ln infinity. Or we just use n again. Yeah, c plus ln n minus by c plus notice the 2n above. So if we have summation of 1 over p equals to c plus ln n as n goes to infinity, we can write 2 over here, and since n is converted to 2n, we can put 2 over here as well. So we have a formula that we can substitute this thing into. So it's c plus ln of 2n minus c plus ln of n equals to s of 2n as n goes to infinity. This condition is still upheld. This n infinity condition is still upheld all throughout. So what now? Well, when we distribute the negative, e is going to become negative. Ln is also going to become negative. So what you expect to see is the c cancels out, and all you're left with is, I'm gonna simplify this thing. All you're left with will be log of 2n minus log of n, which is equal to s2n, again as n goes to infinity. Feel like I have to keep reminding you that. Right, so what now? Well, subtraction in log is same as division, but you put this thing inside. That's just one of the rules. So you see this here, and the n cancels out. So we're left with log of 2 is equal to s of 2n. Log of 2 is equal to s of 2n as n goes to infinity. So just keeps going on and on and on, big number, big number. So we say that s of infinity, or the sum of, so we say that s of infinity is same as log of 2. And there you have it, we've proven that the alternating harmonic series converges to the log of 2 as desired. This actually took longer than expected. So I initially wanted to do both methods in one video, but I think I'm gonna have to split it up. So next video, yeah, it'll come soon. It's a shorter way. Anyway, yeah, bye. Wait, no, not yet. Just want to comment a bit on this method. So what I like about this method is, like I said in the beginning, it explores different areas of math. Like, for example, we found out that the alternating series, which is s of 2n over here, the alternating series can be written as, like the alternating series here, it can be written as a string of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minus by just the first half of that string of numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minus by 1, 2, 3, 4, 5. And that would be the same as saying 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7. And it's cool that you can express an alternating series as a chopped up version of the original harmonic series. So the alternating series is like the harmonic series but just chopped in half, which is interesting to think about. And secondly, we also explored this weird constant thing and also identified that the series of 1 over p here is bigger than ln of infinity by 0.577. So we have a glimpse at different areas of mathematics when we try to answer this question. And I think it's cool that we can also look at different aspects while trying to solve a question that seems unrelated to these different aspects. Anyways, it's really cool to find out that the alternating harmonic series here leads to the log of 2. And yeah, next video soon. See you.